Hello again and welcome to part 6 where we're looking at the production 121GW. I've shown you several non-destructive tests so far. In this segment we're going to be running our potentially destructive tests. I imagine that this video is going to be fairly long, so go grab a bag of popcorn and let's get started. It's getting to be winter around here. Time to put up the motorcycles. Okay, we're back out in the motorcycle trailer. I've got some VP C16 fuel. I'll be applying that to the lens, as well as some of the lettering and the rubber switches. And we'll just see if this fuel attacks the meter at all. Try the different colors. I've only really seen this ever be a problem with these cheap ANIC meters. Let's get our towel out and we'll wipe this off. And you can see it's had no effect at all. They're fun because they've had so many problems with these jacks. Let's just see if this softens the material up at all. It doesn't look like it. We could try the boot while we're at it. Yeah, again, no effect. So that's good. It's a pretty big difference. In this container we have some methanol. This includes a top end oiler. Let's try applying that. Ooh, look at that. There's our problem. Let's try the yellow. I don't know if this will show up in the camera, but there's definitely a little bit of yellow. Let's try our switches. Oh yeah, it's going to strip that lettering right off of there. This isn't even a problem with our ANIC meter. Watch this. See that? I can scrub on this, and definitely, and it basically has no effect. See how that smeared the white? That's a pretty poor deal, because if you work in the garage at all, you can imagine these meters getting exposed to some chemicals. Alcohol's pretty common. Obviously gasoline's pretty common. I would have thought that this fuel would have attacked it long before the methanol. I brought our Q-tip in, tried to get this thing in a little better light. And you can just see that red and yellow hue right up here where I applied it. See how it started to take that white right off? Of course, it started to strip this red as well. See, it's a little lighter now. Tried it a little bit on the yellow, and see it started to strip that as well. Again, I think if you go back and look, I don't think we've ever seen a meter be affected by that methanol. I think this is the very first time. Normally they're affected by gasoline, which kind of makes sense. I mean, that's a cocktail of all kinds of crazy stuff. You'd think if a company like ANIC could even figure out the lettering, certainly a company like UEI that's been around the block would have that lettering all figured out, but it doesn't seem to be the case. That's pretty sad. Alright, this is going to be our drop test. This is roughly a 2-inch thick piece of hardwood. Again, we'll be dropping this meter from roughly 1 meter up, and we'll do it on all 6 sides. You can hear there's nothing shaking in it. Still fires up just fine. So I've gone ahead and functional tested the meter after dropping it, and there doesn't appear to be any problems with the meter at all. So I'd say it survived that test just fine. You can also see that there's no scratches or anything that I noticed with the meter. Looks like the rubber boot did its job protecting it. If you follow my videos, you probably recognize this. This is my temperature chamber. It's essentially made out of a packing box with additional insulation. I'm now using a stack Peltier system to cool this. I have the meter attached to my Fluke reference standard. That's set to 1 millivolt and the meter is set in its millivolt range. What I'm going to be doing is taking the temperature down to -10°C and then up to 60°C, and we'll just see how the meter drifts. I've got the box buttoned up. We'll go ahead and turn on the chamber, and you can see we're currently cooling now. So what I'm going to do is just let this set at -10 for, I don't know, about a half an hour, let the meter stabilize, and then we'll go ahead and change our set point to 60. If we look at the ambient temperature of the 121GW, it's currently displaying a -15.7°C. If we look at our control software, it's showing a -9.44 or so degrees Celsius. Of course, I have a couple of thermocouples inside the box, and the Bryman on the left has one of those thermocouples attached, and you can see it's displaying a -9.5 or so degrees Celsius. So I'm not sure why the 121GW is so far off. I looked in the manual and they don't specify the accuracy of that sensor. Alright, we've been at 60°C now for almost a half an hour. Looks like the 121's internal temperature is still reporting 57.1°C. It looks like it's displaying 929 microvolts versus a millivolt. So the meter has been stabilizing at room temperature for a few hours now. You can see everything is basically back to normal. For the remainder of the testing, we're going to be using production 2. Again, the reason I want to use this meter is I've never taken this one apart, except I did pop off the cover once to look at the circuit board revision. Again, the transient generator contains a step-up transformer that's used to convert our AC line from 110 up to 220. That then goes through a full wave rectifier, and then that can be switched to these outputs. And again, this has some intelligence where essentially if the leads are shorted, this will turn the output back off. So if I take these two leads, I attach them together like so, we turn on the output, you can see it beeps and basically shuts right back off. If I were to turn it on with just the meter attached, there you go, you can see it's reading 227 volts or so DC. Let's just go to AC. Alright, so if I take our Bryman here, I'm just going to put that in parallel with it. It should show 110, and there you go. So this is a similar problem to what I was showing you before, where the meter was unable to show you the DC component of a biased AC waveform. In this particular case, it's unable to show you the AC component. Let's just go ahead and we'll select a different range. A little interesting, so 54 volts, it's still not right. Let's try going up one more range. There you go, 119 volts, that is the correct number. Let's go to the highest range. You can see again 119 volts, that's correct. But in auto range, again the meter doesn't work. It displays 2.2 volts, and obviously that's not correct. Again, I'm surprised that the meter can get certification with these kinds of problems, because I see this as a potential hazard. A full wave rectified AC signal is actually fairly common, and if you had somebody that was assuming this was a safe meter, they attach it up to a bus like this, the meter is again reading nothing, and obviously there's voltage present here, you know, and they go to touch the bus or something thinking that it's off, and indeed it's not. That could lead to a big problem. Let's just try it in the low Z mode. Again, DC voltage is correct. Let's try it in AC. Really? this time it came into AC. So you can see right now, if I select the mode, see, it will not show the DC component. If I turn this on and off again, it's probably going to go to DC. Yep, sure enough. And there's our DC value. That's a pretty crappy setup. You'd think like you could just select the mode and this would switch between the AC and DC values, but apparently they have some intelligence built into it where the meter is supposed to be smarter than the operator, and unfortunately it doesn't work. You should make it work like every other mode where you select the button to basically change the function of the meter. So what we're going to be doing now is just rotating the knob through all the different modes. Again, I don't do anything with the current inputs, and then we'll functional test the meter and make sure that no damage has occurred. So the meter passed that test just fine. You can see I have my grill starter out. Again, this is a very low energy pulse. We'll be applying 5 transients, both positive and negative, with a meter set to each mode. Wow. Again, I wouldn't have expected that to cause a problem with this particular meter. And again, we reverse the polarity just by changing the 2 leads. Unfortunately, I'm not so sure that we haven't already damaged the meter. Let's try going to resistance. Notice how it's not displaying OFL. Let's try shorting our leads out. Look at this. Look at that. Let's try turning it off. We'll turn it back on. Oh. Alright, let's try it with a 10 mega ohm resistor. Does it pick that up? It's reading a little low, but it seems to be okay. Let's try it with 100K. Dead on. Let's just try it with our meg. Again, a little low. I wonder if something's starting to leak. This will be our 40 mega ohm resistor. Again, fairly low. I think we've started to damage the meter. Let's try it in capacitance mode. Again, this will be a 150 picofarads. Normally this would read somewhere around 50 or something. Notice now it reads nothing. Let's try it with a nanofarad. Fairly close. Let's try it with a 0.1. That looks good. Again, this should be roughly 20 millivolts. That looks good. This should read roughly 500 degrees. That looks good. And AC plus DC should be roughly 90 volts. And that looks fine as well. So it looks like we started to damage maybe one of the clamps. I've seen where they'll start to leak before, and I think that that's what we're seeing right now. What we're going to do is go ahead and continue our testing. And you can see I have our homemade ESD gun out. Again, the difference between this gun and this little grill starter is this gun is actually designed around the IEC 61326 standard. A long time ago I had tested a Unity UT181A and I damaged the meter with one poke off of this grill starter. Again, that's fairly common from what I've seen for the Unity brand. They just don't design meters that'll handle a simple ESD event. So in part 2 of that video series, because people were asking, I went through and I characterized this. A lot of people were asking basically what the voltage of this was. Very few people asked about the current. Nobody asked really about the energy. But what I did is I showed you how I captured the event off of this, and I overlaid that against the IEC standard. And you could see that essentially the pulse coming off of this was hardly anything compared to what the standard actually calls for. So I developed this gun to get us a little closer to what the standard was. So we're going to be using this to apply 5 pulses, both positive and negative, again in each mode of the meter. And then like before, we'll functional test it after we're done. So here we go. Alright, here's with our short. Again, this will be our 10 mega ohm. I'll go through and finish functional testing it. We're going to begin our transient testing. Currently our oscilloscope is set for 500 volts per division. You can see we're 2 divisions up, or 1000 volts peak. It's set at 100 microseconds per division, so this is a 100 microsecond full width half height. This is where we'll start. And you can see the oscilloscope is attached to our high voltage probe, and that's just connected to the output of the generator. It'll basically be in parallel with the meter. Again, over the years, had a lot of stupid comments. People have suggested that I'm basically discharging capacitors directly into the meter. Obviously that's not the case, or we wouldn't be seeing that waveform. So that waveform is shaped by the output network of the generator. Again, any energy that's not being absorbed by the meter is absorbed in that output network of the generator, and it's just given off in heat. Again, this transient generator has a 2 ohm source impedance. We'll be applying 5 transients, both positive and negative, with the meter set to each mode. Alright, here we go. I think the prototype meter had failed at 2000 volts. I had promised Dave that I wouldn't include that data in the spreadsheet, so you'd have to go back and look at the original video for that, but I think that's where it failed. With this meter having a whole different clamping scheme, it'll be interesting to see if it actually fails around that same area. Again, this generator is only capable of putting out about 20 joules. It's not much energy at all. I actually had made a video because a lot of people, for some reason, equate this testing to safety testing, which it certainly is not. Again, to invert the polarity of the waveform, I just flip the leads around. Alright, that's it. We'll go ahead and functional test the meter. Let's just take it to resistance real quick. Oh. Wow, look at our 1 meg now. Here's our 10 meg ohm. You can see it's 8.5 meg. It's really getting bad. This is going to be our 40 mega ohm, all the way down to 34 meg. So I finished functional testing the meter, and this is our 1 nanofarad capacitor. Again, this used to read fairly close, so the meter is continuing to degrade. Obviously the meter was damaged with that first ESD pulse off the grill starter, but I'd like to continue to test at some higher transients. So again, our scope is set for 500 volts per division. You can see we're now 3 divisions up, or 1.5 kV. Again, this is 100 microseconds per division, or 1 division over, or 100 microsecond full width half height. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. We'll just start in the low Z. Again, a lot of the meters that I've looked at that have survived some of these basic tests are normally rated for IEC 61326. That's an EMC standard. I know the 121GW has been certified for the safety standard. That's 61010. That standard calls out things like surge testing and stuff for a lightning strike. 61326 will call out things like ESD, for example. A lot of people will post about testing the meter with the leads that are supplied with them. Actually, there's a separate IEC standard for the test leads. And that's it. And let's just switch this over to the capacitance mode. I've just got this attached to our 1 nanofarad capacitor. Looks like it's about the same. Let's just try resistance real quick. I mean, the leads are open right now. See how this thing's having trouble trying to lock into even the open leads? Here's our 10 mega ohm resistor. You can see it's continuing to degrade. It's pretty bizarre. Again, I don't remember the prototype having any problems like this at 1.5 kV. Let me go through and I'll finish functional testing it. So I don't see any other problems with the meter. So I changed the scale of our oscilloscope to 1000 volts per division. Again, it's still at 100 microseconds. You can see we're now 2 full divisions up, or 2000 volts peak, and still at the half height. You can see it's 100 microseconds, or 1 division over. Again, we'll be applying 5 transients, positive and negative, with the meter set to each mode. Again, this is where we had damaged the meter before. Let's just see how it fares this time. I can hear something breaking down in the meter. Tell you what, I'm going to turn off the oscilloscope. Let me get the camera a little closer to it. Let's see if you can hear this. Hear that? Something's breaking down in this. Shoot, that's only 2000 volts. That's where the meter failed before. Let's just see if it'll read resistance right now. Again, this is 10 meg. Look at this. Let's try resetting the meter. Yeah. Again, that's a 10 mega ohm resistor. Let's try it with a short. Okay, that seems to work. Let's try it with a 1 mega ohm. Oh, right there, 500K now once it's downranged. I would say our meter now is definitely dead. Let's try some of the other modes. So, again, this is continuity test. That seems to work. Diode check. You can see it's reading 2.28. Again, that's with an open. I'm going to turn off the generator so we don't get poked. Let's try it in capacitance mode. Again, this is our 1 nanofarad capacitor. Yep. You can see it's not going to read that. Let's just try it in our frequency mode. Again, this should be 60 Hertz. And this should be 60 Hertz. And you can see we're reading nothing. Alright, I'm just going to place our Bryman here in parallel with the 121. This should be roughly 60 Hertz. And you can see the 121 is not reading anything. And of course, my Bryman is plugged right into those leads. So let's just try it at a different frequency real quick. This will be 120. You can see no effect. Let's try it in the millivolt range. So this should be roughly 20 millivolts right now, and you can see it's basically reading over range. Let's just go ahead and I'm going to remove these leads, and you can see even with our leads not attached, I mean they're going basically to the 121, and again our Bryman's right in parallel with it. You can see that our 121 is actually driving voltage out in the millivolt mode into our Bryman. So let's have a look at what voltage we've got. So the 121 is currently driving out 1.65 volts. Let's just see what kind of current we're talking about. We'll set this down to the microamps. A fair amount of current, about 560 microamps. Let's just try it in the DC voltage mode. So this should be roughly 60. And this should be roughly 70. This should be about 90 volts of AC plus DC. Looks fine. So it looks like our resistance, the frequency, and the millivolt functions have all been damaged. I'll go ahead and finish looking at the rest of the functions. This is looking at our spreadsheet, and you can see I've gone ahead and added the data for the 121GW In the first column, this is our 1000 volt DC test. The meter passed that just fine. The second column is our 220 volt rectified signal, and the meter passed that just fine as well. Again, some meters have actually failed that test, including a Tech Power TP2844R. There's a Unity UT20B. The TPI Summit 194.2 failed. Again, that's the meter that we just repaired for these videos. Another meter that had failed was the Mastech MS8211 and also the OWAN B41T. The next column is our grill starter. And of course, quite a few meters failed that. A lot of those are Unities, so the UT61D, the Unity 61E, the X-Tech EX430, the Vichy VC99, the Unity UT181A, the Meter K MK01A, and to add to this list, the 121GW. Again, just to recap, while running the grill starter test, we caused a fair amount of leakage to occur somewhere in the meter, which was throwing off the readings. And as I continued to test the meter continued to degrade to the point where it basically became unfunctional. And that happened at 2000 volts. So I've added a note saying high leakage after grill starter causing errors in reading, continued testing the meter to full failure. So again, if you go back and look at the original test that I did with the prototype, the original prototype had actually survived all these tests up to 1.5 kV, and then it was damaged at 2000 volts. I'm assuming that the way that they're now clamping the meter just isn't as robust as what they had with the prototype. So next we're going to be running our live test on the rotary switch. The only time that I've had this back cover off on this particular meter was again just to make sure that the hardware was the same as Proto 1. Here we have Proto 1. I haven't had this apart since the very first time for our show and tell. Hopefully this will show up on the camera, but have a look at the amount of wear that's already taken place on these contacts. You can just see the stripes right down the middle of the contacts. Again, the prototype meter, which had different contacts and stuff, had a lot of problems with the switch. This has been my primary concern with it. David posted how the new design, they finally plated this hole. You would have thought they would have done that from the get-go, because again, this is essentially the bearing surface, and you've got this clip that expands, and this is quite tight riding inside of this glass hole. And of course, once they route this out, this is a pretty jagged edge, so you can imagine that that's going to erode this plastic fairly quickly. It'll be interesting to see how this test goes. You can just see, like right along here, see the marks that we're already leaving. I think what I'm going to do is use our reset contacts. Again, that's these two outside ones here. One of those attaches to VSS and the other one the reset pin. You can see we have fairly good access to those. So what we'll do is take production 2. We'll just pop that back cover. We won't actually remove the circuit board still. Again, what I'm trying to do is keep those contacts in basically the same condition that they were in when the meter was supplied to me. And we'll just tack a couple of wires right in there. Again, this meter hasn't been exposed to anything that could damage it. My plan was to keep this meter fully functional for any future test that we may decide to run with it. So again, a lot of the meters, they'll use a lubrication on these contacts. Again, these meters use a dry contact. You see a lot of crazy things posted about lubricating the switch contacts. I've seen people talk about using spit, Vaseline, WD-40, all kinds of crazy stuff. You know these people are complete idiots, right? So is there a benefit to the meters that have the lubrication in them? Maybe. We've certainly seen some pretty crappy meters that had lubrication that did very poorly in the life cycling test. On the flip side of that, we've seen some pretty nice meters that had no lubrication perform really well on the test. I think it just depends. Again, this is production 2. Let's go ahead and pop the cover. Again, I've only had this off of here one time before. So to run this test, we'll be doing this without the batteries. What we'll do is just run these things right through the case like so, just to make sure that we don't cause any heat damage. I'll just rotate the switch away from those set of contacts. You can see I just tacked them right in through those two vias. You can see I've added a little tape around the fuse here. That's just going to be our strain relief. Again, we'll reattach our back cover. See, our switch is working. I'm thinking what I'll do is just run these right along the edge here, right like that. Maybe make sure the leads are spread apart a little bit. Just run the wires out the back like so, and I think we're good to go. Then what we'll do is put our little spacer in here just to prevent the meter from rocking around too much. And let's just have a look. Looks good. And there we have it. I think we're ready to set up our stepper motor next.
And we've actually hooked up some wires here to the off position of the unit. So when it's in the off position, we'll actually be able to measure the contact resistance here, but we've actually changed our jig over here to actually measure this. So we're using an ADC on here with a parallel resistor in there, a divider resistor, and then a parallel resistor just in case it opens, and then we can calculate the actual contact resistance. What does our contact resistance go up to, David? About 10 ohms. Anyway, we've tested it, and our nominal contact resistance is about 0.9 or something like that. So, of course, we expect that to vary a lot and change as we cycle through the automated testing. But anyway, we're going to try it with the new shim, get our automated tester, and whack it in there. So, let's give it a whirl.
So the first thing we're going to do is align the meter. We do that by placing the switch basically in the center somewhere. Software is going to reduce the amount of current until it figures out basically what the stall current is. It'll then look for the two ends. After that, we're pretty much ready to go. Again, no hocus pocus, no yellow sticky notes, no conversions. All of our measurements are just done with standard off-the-shelf equipment. Meter now has about 2,000 cycles on it, just a little over. You can hear our switch grinding just a little bit. Get an idea how loose our fingers are. You notice that they don't touch the face. We don't want there to be any kind of a bind. Again, I'm not too surprised by the squeaking, you know, with the shim and everything in there. And again, to be clear, this meter has not been apart. This is the way it was supplied straight from Dave, so the meter is about halfway through, and I thought I'd just stop the test momentarily. I wanted to show you what this thing does, and I want to bring the camera in really close. Hopefully you'll be able to hear this. So I just want to rotate the knob. Hear how it squeaks? See, it just doesn't click. And it's got this definite squeak. Again, this is production 1. Hear how nice that snaps. Of course, there's no signs of any squeaking either. Again, I'm not going to take this meter apart until we've actually completed the cycling. So I'll just go ahead and set this thing back up and start it running again. So the meter has about 40,000 cycles on it right now. You can hear basically it doesn't click at all anymore. Compare that with this one. You can Here it's still grinding quite a bit. Alright, so we finished our life cycle test. Let me just remove the meter from our jig. Again, there's no batteries or anything in the meter, so we can't power it up. But let me bring the camera in a little closer. Compare that with production 1. Let's just use the other 121 to look at the contact resistance real quick. See, it's not very stable. Maybe call it 250-ish ohms. Let me try pushing down a little bit. There's an ohm. Again, this started out maybe a half an ohm or so. As soon as I take my finger off it, you can see we're up to 4 ohms. Yeah, let's try the other side. Looks the same. Because there appears to be a fair amount of wear in the detent spring, we'll be taking the entire switch assembly apart. My plan is to do all this under the microscope. Again, my microscope is a bit of a kludge. You can see these mounts. This is all handmade. It's quite a mess. Anyway, I've got this new head. This one's made by Olympus like the old one, but this is a little newer. This one's probably made in the 70s. My original one was probably made in the 50s. We'll be using this to look at the spring contacts. So let's go ahead and we'll start taking this thing apart. I'm sure that a few of you are curious if this meter will still power up. Let's just have a look. Oh, boy, that switch is pretty touchy. See if it'll come on. Oh, come on. There you go. Fortunately, we can't functional test the meter because, of course, it's been damaged by that grill starter and, you know, later off of our 2kV transient, just like the prototype. But it does look like the meter could be somewhat functional. It's not something you'd probably want to rely on after all this. I mean, right there you can see it. It's powered off again. Just a slight push. Comes right back up. You can see, like, I'm not putting any pressure on it really. It's off. I mean, it's just, you can see it's just on the cusp of wanting to work. Now if I push on it a little bit, oh, I mean, right here I'm applying pressure. Right there it came on. I mean, I'm putting a lot of pressure on that switch. There, I'm off. And here I'm on. Yep. Alright, let's go ahead and we'll finish taking it apart. I was expecting a lot more erosion in this area than what we're seeing. This looks pretty good, actually. Looks like it's still fitting pretty tight on the shaft. Ooh. Notice how the shim has been installed? I think in Dave's video he has this thing flipped upside down.
The new shim provided by UEI, yes, it does actually have a routed out little bit in there. It's actually very nice. Those little tooling holes there are designed to get the rounded edges. Yes, it's made out of regular FR4 fiberglass, and that is going to sit. Whoops, sorry, we've actually got this hooked up. I'll show you in a second. But that actually just sits over. Yeah, sits over there like that, and that just wedges in there nicely. And it goes back in along with the new knob, of course.
So I'm not really sure what direction that would go. I'm almost thinking that when he showed it flipped, he was concerned about it, you know, touching up against that C-clip. You can see it rides pretty flat. Then I thought maybe they relieved it for this little lip right here. This area right in the center looks like it's a little proud. Right there, you can just see it. So I think that this shim is installed correctly. And just in Dave's video he showed it, I think, installed upside down is all. Let's see how much slop is in that. Yeah, I think we should take this apart next. Let me take a couple of good pictures of this. It's definitely been polishing that surface a little bit. I don't feel any grooves or anything at all like that on this shim. As far as the plastic, oh yeah, right there. This is just shaving this plastic right down. There is definitely a lip. I mean, that's pretty high up. That's removed a lot of plastic. Yeah, this is why it's no longer clicking. You see how it's eroding the little cams off? Unlike the key sight meter, it doesn't look like it cracked any of the prongs. I'd have to take the other meter apart and take some measurements to tell just how much these have worn down. Just use the end of our needle nose here to compress our 3 prongs. Oops. One of the things I should point out is when Dave had done his life cycle testing, the meter that he shows has 2 dimples in the outside contacts and then a single dimple for the 2 inside contacts. You notice on this one, like the other meter that I have, it's a single dimple all the way across.
Okay, let's have a look at the contacts first of all. And the contacts are actually, the contacts look very good, and you can see the dust caked under there. But for 25,000 cycles, those contacts look really quite nice, so that doesn't seem to be a problem.
So they've changed the contacts on this. This is looking at the 121GW's upper housing. What I'd like you to look at is this area right here where the detent spring rides against these teeth. You can see quite a bit of wear. A lot of material has been removed. You can see what these lobes are normally shaped like, where the detent spring isn't riding on them. Again, as I kind of rock this in, you see how much material has been removed. This isn't something I would have expected. David made a comment that they had changed the detent spring.
Alright, so I've got the new meter together with the new knob and the new white plastic spring indent thing in there, plus the new shim.
He didn't elaborate on the reason for that, but I wonder if it had something to do with this. Let's have a look at the detent spring. Again, notice the amount of material that's removed off of these little nubs here. They're all pretty much the same, I would imagine. Again, these are pretty wore down, but at least they didn't crack like the key sight meter. This is looking at the shim, and this is the side that's rubbing up against the case. You can see this little lip where it looks like the material is building up. This is actually flat. These are not scratches, that's just my fingernail rubbing this thing. This is looking at the front case half. This is the area where that shim rides. Now this area right here, that's the lip. That's where all that material is coming from. I'm just going to take a cotton swab and just run this right across this area. May not look like much, but considering how much material had to be removed to cause that lip, that's where all this dust is coming from. Here we're looking at the circuit board. You can just see how much wear is taking place. In this area right here, that's a fairly deep groove getting cut. Basically, it looks like what's happening is that contact is bouncing down inside this groove, and then it's got to lift up, and that's just causing this ramp. I mean, those are fairly deep. I'm not sure how well this is going to show up with the camera. Let me just try to zoom into some of this. You can see a lot of this is metallic, which you would expect. I mean, that material has to go somewhere. Now, hopefully this shows up, but you can see that's a definite metal shaving, and there's quite a few others you can see, like right here in the center of the screen. That's all copper. Up here, again, more shards of copper. Here's another piece right along the edge. Of course, when you're seeing this kind of wear, that material has to go somewhere. Here's another nice big sliver in the middle of the screen. Again, you can see a couple of shards right here, but what can happen, you can see the amount of buildup between these two switch contacts. That's all copper, and you can see that's not unique to this one pad. Like here you have the same thing. Again, it's almost shorting out the two pads. So what can happen is you start to apply high voltage to the meter. These areas could actually cause the meter to break down where it wouldn't normally. And of course, that can lead to other problems. Let me just zoom in all the way, see if we can get a better shot of this. These are almost like metal flakes. See right in the center of the screen versus this piece here. It's almost like whatever happened here just peeled this little piece right off. Well, it doesn't look very good. Let's have a look at the wiper contacts. These have a fair amount of wear on them. They're basically flat. I'm not too surprised by this. Again, just looking at how that metal's being peeled off. That's because of this sharp edge that we've created. Notice this contact right here, it almost looks like it has a little bit of a lip on it. It sure does. My guess is the majority of that contact is riding on the pad, but part of it overhangs, and where it does, it's caused that lip. That gives you an idea how much material has been removed. And again, that's all had to deposit somewhere, and that's why we see so much metallic material on the circuit board. Again, they changed the design of the contacts. Some meters were sold with double dimples on the outside contacts. I think I've seen them with all four contacts being double dimples. This particular meter is all single dimples. This is looking at the software that we use to cycle the switch contacts. Let's just add the data that we've collected for the 121. So vertically, we're looking at resistance. I'm rotating the switch fully clockwise and then counterclockwise, and I consider that one cycle. So 50,000 of my cycles would equate to 100,000 of Dave's cycles. Let's just zoom in a little bit. You can see we're reading about 400 milliohms for the first 300 cycles. Then you can see it increases to about 420 milliohms up till about 800 cycles, and then it starts rising, and you can just see as we continue to run it, the meter just continues to degrade. If you're interested in seeing how the other meters compare against the 121, let's just load up all of our data. This is what it looks like. You can see I clipped the data at 1,000 ohms. The blue trace here, this is our free meter from Harbor Freight. This gold trace is an ANAG meter. This one was resold under the KainkaLabs brand. It's the ZT102. The yellow trace is our EOSUN. This is a model EM129. And then our white trace, this is the Agilent UT1231A. So it looks like our 121 does pretty good, but again, let's compare it against the other meters. So this is zoomed in now, and the blue trace is the 121GW. Again, let's just zoom in a little bit. This green trace is our Bryman BM869S. You can see we reached a maximum of about 1.3 ohms. Compare that with the Bryman BM839S, and it looks like that hit about the same resistance. But let's look at our Fluke. You can see that Fluke 17B Plus just basically stays flat. And when we took that meter apart, there was no signs of any damage, and there was hardly any wear at all. Again, that meter is made in China, and you can see regardless of where they're producing the meters, Fluke really knows how to design a switch. Again, this is the 17B Plus. Here's the 121GW. And here's our two Brymans. This is looking at the accumulated data. Again, the blue here is our 121GW. So again, this is taking every resistance reading for the 50,000 cycles, and it's accumulating those values. Let's say we had a meter that read 0.1 ohms and we cycled it 50,000 times. We'd expect to see a linear line going up to 5,000 ohms at 50,000 cycles. Let's go ahead and look at the log data. Both the vertical and horizontal scales are logarithmic. In the horizontal, we're looking at resistance, and in the vertical, we're looking at the number of make-break cycles. Obviously, the best meter is going to be 0 ohms for the full 50,000 cycles. We haven't seen anything like that. For now, the Fluke is the best meter we have. Again, that would just basically look like a horizontal line across the screen. The whole reason that I added these lower numbers was because originally that's what the Fluke looked like, was just a flat line, and people were complaining that essentially it's not a perfect meter and they wanted to see this data down here. But, you know, the reality is at 0.01 ohms, that switch is basically perfect. So for the few meters that we've looked at so far, obviously the 121 isn't nearly as good as what the Bryman meters are, and certainly not even in the ballpark compared to the Fluke 17B Plus. So I've gone ahead and I've cleaned up production 2. During the transient testing at 2 kV, I thought I heard something breaking down inside of the meter. I thought now that the meter's clean, we could try to see where it's actually breaking down at. So let's just go ahead, we'll connect up our transient generator. Oh, look at this, right up here. Let's get our other camera out. And you can see where it's breaking down. It's right in this clamp area again, which is one of the things that they've changed numerous times. So again, the prototype meter had survived that grill starter just fine, and it also survived all the way up to 1.5 kV. Obviously, this meter couldn't survive those same transients. With UEI having made meters for such a long time, I'm not very impressed with it. Just to summarize some of the things that we've looked at during this series, one of the big problems I saw with the meter is that it couldn't resolve the DC component of a DC biased AC waveform. And of course, during this test, we had a full wave rectified AC waveform at 220 volts, and the meter couldn't resolve the AC component. I'm surprised that the meter could have ever got safety certification with those problems. I was also very surprised when we exposed the meter to methanol, and I realized that it strips the lettering. Again, I believe that this is the only meter that I've looked at where the lettering was actually the problem. We've seen some of those cheap ANIG meters where we've etched the screen. Again, this just isn't something I would have expected to run across. Obviously, the firmware has a long way to go. The fact that the meter is released to production and people are still finding problems with the meter. A recent one was that the meter could not record to the flash card. And several of us, including Dave now, has repeated that test, and sure enough, there are some problems when recording to the SD card. So again, new problems cropping up, and the firmware changes continue on. Not what you would expect from something that's in production. Maybe you'd expect to see a minor bug here and there, but nothing to the likes of what we've seen with this meter. To me, it looks like the switch has been a problem since the beginning. Again, the prototype meter, that switch had a lot of damage with very little cycling, and we can see now we have this addition of a shim. It doesn't seem like it was well thought out because it's rubbing against the plastic case and it's eroding all that plastic. We heard Dave mention about changing the detent spring, and you could just see the amount of wear that that detent spring has caused with this particular meter. And of course, I've talked about this before, how they've changed the spring contacts now numerous times. And of course, we're seeing quite a bit of wear with this. And worse, we're seeing metallic debris up around the contacts of the switch. And this is not something that you want to see in a safety device. Personally, I think this meter has way too many problems to be considered anything more than a gimmick. I think the real selling point is this logo right here. You start looking beyond that. The fact that it failed on the grill starter of all things. Most of the meters that I've seen fail that grill starter are the Unity brand. I would put this particular meter right in that same class. You know, all this stuff could have been avoided. You have to believe that a company like UEI with their resources could do a better job than this. Again, Dave did announce that they have a newer version. I'm not sure why they continued to sell these old ones. Again, that wasn't made clear on his website when I placed the order. It's hard to say if the new meter would do any better. Again, we know that they've changed both of these clamps. Maybe it would hold up, maybe it wouldn't. But the way that this particular meter was constructed, it's obviously not very robust. Well, that's going to be it for now. Hope all of you have a wonderful holiday, and we'll see you in the next video. Later. Again, the way this works, the high voltage transient generator is going to put a high voltage spike across the meter. That's going to arc at the same time that that arc is happening. This is going to trigger up our half cycle line simulator. Again, this is a very low voltage generator, but it has a fair amount of energy. Where this is 20 joules at most, this can put out about 600 joules. Now again, remember what I said is normally what happens is the meters don't break down at all. And all the energy is dissipated in the output network of this transient generator. And that's typically what will happen. Most of the meters, like pretty much every Fluke that we've ever looked at, the Brymans that I've looked at, you could run this same transient that I'm about to show you. This test would have no effect whatsoever. And again, that's because this high voltage transient generator can't break down those meters. Not the case with the 121. Problem with making videos like this is you really only have one shot at it. So if you make any mistake, there's no do-overs. So I'm just double checking everything. Alright, we're clear to go. Well, that wasn't very spectacular. I can definitely smell it. I don't know if this will show up on the camera, but it looks like all we've done here is just cook this one resistor. Let's just pop the board out real quick. Let's just have a look at our switch. Oh, right there. That's why I smell circuit board burning. Again, 600 joules, it's a lot more energy than what I'm capable of putting out with my small generators, but obviously it's nothing compared to a real line fault. And that's why I say that these tests really have nothing to do with safety. Let's just clean up that area of circuit board real quick. It's definitely got a little divot in there now. And just put our switch back in real quick. Slide our meter back together. Just pop the cover on. Let's see if this thing will even power up. there you go, 2.02. I'm sure electrically I could go in and repair this meter. Obviously I've done that with the prototype meter, but with the amount of wear and tear on this particular meter, I probably won't do anything more with it. I probably won't recycle this meter just in case there's some other destructive test that we decide to run later on.